Hello friends, welcome back to my YouTube channel. In the 22nd part of my discussion on adsorption, I will be discussing a second numerical example that is based on the application of the Freundlich adsorption isotherm to a multi-stage countercurrent adsorption operation. Why this is the second numerical? The first one I had discussed in part number 21, the previous video on this topic. I am giving link to the playlist that has all my videos on adsorption in the description section. In the previous part, I had discussed how to get the quantity of adsorbent that is required in a two-stage countercurrent adsorption operation. I also discussed how to get the minimum quantity of adsorbent that can be used in that operation. And for that, I had used the graphical method to get those quantities, the quantity of adsorbent required in a two-stage countercurrent operation and the minimum quantity of adsorbent that can be used in that operation. So equilibrium data, it is given to us. If it is given to us, you can plot it as per the requirement and then you can solve as I did it in the previous part. Now in this particular part, I will tell you how you can get the minimum adsorbent to solvent ratio if you know the equation of the equilibrium curve. And by using the equation of the equilibrium curve, how can you get the minimum adsorbent to solvent ratio that can be used in a typical multi-stage countercurrent adsorption operation? So let us begin the discussion. To start with, we will look at the numerical statement. You have a batch of kerosene containing dissolved water at a concentration of 40 ppm, that is parts per million, is to be dried to 5 ppm by contacting with dry silica gel at 25 degrees Celsius. The kerosene density is 783 kg per meter cube and the equilibrium distribution coefficient, it is given by this equation. 0.522 is equal to capital C upon capital X, where capital C is kg water per meter cube of kerosene and capital X is kg water per kg gel. So with this data, we are supposed to find the minimum adsorbent to solvent ratio that can be used in this particular operation. So you have a batch of kerosene, and what is the problem with this batch? There is some dissolved water in it. So initially the batch is containing a dissolved concentration of 40 ppm, 40 parts per million of water. And we have to reduce it to 5 parts per million, 5 ppm. And how is that done? It is done by contacting with dry silica gel. That is, the adsorbent that is used in this case is dry silica gel. And when they say it is dry silica gel, that means it is fresh adsorbent. That is, it's not containing any water on its surface. The operation is to be carried out at 25 degrees Celsius. That is, it is done at a constant temperature. Then the density of the kerosene, it is given to us, it is 783 kg per meter cube. And the equilibrium distribution coefficient, it is given to us. And the equation for the distribution coefficient, distribution at equilibrium distribution coefficient, it is 0.522, that is equal to capital C upon capital X. Capital C is kg of water per meter cube of kerosene and capital X is kg water per kg silica gel. That means this is the equilibrium relationship that is given to us. And what are we supposed to find? We are supposed to find the minimum adsorbent to solvent ratio that can be used in this operation. So let us move ahead. First of all, we will list what is given to us. So water dissolved in kerosene, it is to be reduced. Water that is dissolved in a batch of kerosene, it is to be reduced. How it is to be done? By adsorbing it on dry silica gel. The concentration to be reduced from 40 ppm to 5 ppm. So concentration of water in kerosene, it is to be reduced from 40 ppm to 5 ppm. The equilibrium relationship is given to us. It is 0.522, that is equal to capital C upon capital X. Capital C is defined in this way, capital X is defined in this way. Then in this case, in this equation, C is the concentration of water in kerosene on water-free basis. You can easily understand. So this is kg of water per meter cube of kerosene. So by describing this concentration, water is not considered in the denominator. So that's why capital C is concentration of water in kerosene on water-free basis. Then you have capital X, which is weight fraction of water on the surface of the gel on water-free basis. You can easily understand. Capital X is kg water per kg gel. So this is weight fraction of water on water-free basis on the surface of the gel. So that is capital X. So here the concentrations, they are given on solute-free basis. Why solute-free basis? Because in this case the solute is water. So the concentrations that are given in the equilibrium relationship, they are on a solute-free basis. We need to understand this. Then density of kerosene, it is given to us. Let us denote it as rho. So rho is 783 kg per meter cube. What is the objective? The objective is to find the minimum adsorbent to solvent ratio that can be used in this operation. That is, we are supposed to get SS minimum by ELS. You please understand this thing. We are not getting SS minimum. Rather, we are going to get, or we have to find the ratio, minimum adsorbent to solvent ratio. That is, we are supposed to report the value of this ratio, SS minimum by ELS. So for the theoretical aspects I have discussed in my earlier videos, I have given link to the playlist of all my videos on adsorption. So you please watch it in order to know what are the notations. If you have not yet seen that video, you please watch it and you can understand the notations over there. Okay, so let us move ahead. The objective is to find the minimum adsorbent to solvent ratio, that is SS minimum by ELS. Now what would be the approach for solving this numerical? First, we are going to write the equation of the operating line in terms of C and X. So in my discussion on multistage counter current operation, I had derived the equation, but that was in terms of capital Y and capital X. In this case, capital X is you can use as it is, but C you have to bring in the equation of the operating line. So first step would be, we will get the equation of the operating line in terms of capital C and capital X so that we can use it. Then we will convert the ppm data, parts per million data, that is concentration which is given in ppm. We will be converting it to kg water per meter cube of kerosene. Kg water per meter cube of kerosene. So initial ppm, we will convert it to C naught. So this quantity will be this quantity is C, and for initial ppm it will be C naught, and for final ppm it would be Cn. So first we will be converting the initial ppm to C0 and then the final ppm to Cn. What is C0? Kg water per meter cube of kerosene initially present in the solution, and Cn is kg water per meter cube of kerosene that would be present in the kerosene after the end of the operation. So that would be the second step. And then we will get the coordinates of the pinch point. Since we have to get the minimum adsorbent to solvent ratio, we need to get the coordinates of the pinch point. So pinch point is the point where the equilibrium curve and the operating line intersect each other. And what are the coordinates of this pinch point? These are x1 max and C0. If you plot C versus X, if a graph is plotted where C is plotted on the y-axis and X is plotted on the x-axis, so you will be getting a pinch point. The pinch point on this graph, it will have coordinates of x1 max and C0. So in order to get the minimum adsorbent to solvent ratio, we need to get the coordinates of the pinch point. So that would be the third step. Again, what is pinch point, and then what is minimum adsorbent to solvent ratio? You please refer my videos on these topics. As I said, link to the entire playlist is available in the description section. So for that, what we will do, what information is useful to us, let us understand. First thing is, if you look at the equilibrium relationship is 0.522 is equal to C upon X. So that is C is equal to 0.522 into X. So it is a linear equation. What is the meaning of this? The meaning is the equilibrium curve is a straight line. The equilibrium curve is a straight line. And if the equilibrium curve is a straight line, then pinch point, it is going to occur at the concentrated end. So pinch point will be occurring like this. Let me show you in this graph. I have shown it. I will show it after some time. But just now let me tell you. So the equilibrium curve is a straight line and the operating line will be intersecting the equilibrium curve at the concentrated end. So this end of the operating line is the concentrated end, and this is the operating line will be intersecting with this equilibrium curve, which is a straight line at the concentrated end. So this is the pinch point, and this point is going to have coordinates of x1 max, because that would be the maximum possible concentration on the surface of the adsorbent, x1 max and C0. So in this way, you have to get the coordinates of the pinch point. Then once you get the coordinates, you have to solve the equations of the operating line and the equilibrium curve simultaneously to get the minimum adsorbent to solvent ratio that can be used. So after solving the equations of the operating line and equilibrium curve, we can get the minimum adsorbent to solvent ratio. So that would be the approach. First, we will write the equation for the operating line in terms of C and X. We will convert ppm data to C0 and Cn. Then we will get the coordinates of the pinch point, and then we will use these coordinates in the equation of the operating line to get the minimum adsorbent to solvent ratio. So I hope you must have understood the steps that I will be following for solving this numerical. Let us move ahead. So first step is we are going to get equation of the operating line in terms of capital C and capital X. So for that, let me show you the operation. Over here, I have represented the entire operation entire multi-stage counter current adsorption operation by this rectangle. So what is the input? Input is the kerosene that is containing water in it. So the feed, it is identified by these parameters. Again, in order to know about this notations, you please refer my earlier videos. And then it is contacted with the adsorbent in a counter current fashion. So the adsorbent will be identified by these parameters. Then kerosene, after the concentration of water in it is reduced, it will be coming out, and when it comes out, it will be identified by these parameters. And then the adsorbent, after getting water on its surface, it will be coming out of the operation, and then it will be identified by these parameters. So when you have a counter current adsorption operation that is containing capital N number of stages in it, then the equation of the operating line is given in this way: capital Y0 minus capital Y1 Yn divided by capital X1 minus capital Xn plus 1, that is equal to SS upon Ls. So Y0 is weight fraction of solute on solute free basis in the inlet feed. Yn is weight fraction of solute on solute free basis in the outlet stream. X1, it is weight fraction of solute on solute free basis on the adsorbent phase that is coming out of the operation. And then Xn plus 1 is weight fraction of solute on solute free basis that is entering the operation. SS is the mass flow rate of the solid adsorbent in the adsorbent phase. Ls is the mass flow rate of unadsorbed component in the feed solution. So all these notations I have discussed in detail in my earlier videos. You please, if you have not yet seen that video, you please watch it. So when you have the operation in this way, where the streams are defined with these parameters, then the operating line on a plot, the operating line on XY plot, where capital X is plotted on the x-axis, capital Y is plotted on the y-axis, the equation of the operating line is in this form: capital Y0 minus capital Yn divided by capital X1 minus capital Xn plus 1 is equal to SS upon Ls. So now the task is, we will have to convert it to the form that is required in this particular numerical. So let me show. So in this case, the inlet feed solution, it will be, the concentration is given by C0. So in this way, the feed is entering into the operation. And then for the adsorbent phase, the concentration that is being used in this numerical, there is no need to change it, because we are going to use as it is, because it is given as weight fraction of solute on solute free basis, that is capital X. Then the liquid solution, the kerosene that will be coming out, it will be having concentration of Cn. What is capital Cn? Capital Cn is concentration of water on water free basis. C0, concentration of water on water free basis. And for the adsorbent phase, it will remain as it is. So that means in this case, how the equation is going to change? The equation y's, all y's in the equation, they will be replaced with c's. That is the difference. So the equation now, it will be written as C0 minus Cn divided by x1 minus xn plus 1, that is equal to SS upon Ls. So if you write material balance, solute material balance, then if you express it in terms of concentrations on solute free basis, you are going to get this equation. So in order to get this equation, you can follow a procedure that is similar to the one that was adopted or that was used in getting this equation. I have derived it in my discussion on theoretical aspects of the multi-stage counter current operation. You please watch that video. Okay, so henceforth now we are going to use this equation in our discussions. Capital C naught minus capital Cn divided by capital X1 minus Xn plus 1, that is equal to Ss upon Ls. Let us move ahead. So this is the equation. So the objective for this step was to get the equation of the operating line in terms of capital C and capital X, and now we have got that equation. So that ends our job for the first step. Now let us move on to the next step. Next step is we will be converting ppm to C, capital C, concentration, which is given in ppm. Now we will convert it to capital C. What is capital C? Capital C is kg of water per meter cube of kerosene. So ppm we are going to convert to capital C. And for that we know 1 ppm of water in kerosene, concentration of 1 ppm of water in kerosene is 1 part of water in 10 to the power 6 parts of water plus kerosene. So in 10 to the power 6 parts of water plus kerosene, there is 1 part of water in it. 1 part of water per 10 to the power 6 parts of water plus kerosene is 1 ppm. 10 to the power 6 is 1 million. So it would be parts per million. That means 1 ppm of water in kerosene is equal to, if I express it in kgs, so it will be 1 kg of water in 10 to the power 6 kg of water plus kerosene. So that is simply weight fraction of water. So that means 1 ppm is equal to 1 upon 10 to the power 6, which is 1 into 10 to the power minus 6 weight fraction of water in kerosene. So initial ppm is 40. So weight fraction we are denoting it by capital small x, and weight fraction on solutary basis we are going to denote it by capital X. We know that. So initial ppm is 40. So that means Y0. Now the weight fraction of water in kerosene we will be denoting it by small y, and weight fraction of water in kerosene on water free basis we will be denoting it by capital Y. Okay. So initial ppm is 40, that is Y0 is 40 into 1. So 1 ppm is 1 into 10 to the power minus 6 weight fraction. So therefore 40 ppm will be 40 into 1 into 10 to the power minus 6. And that is, you can write Y0, small y0 is equal to 40 into 10 to the power minus 6. So in this way, we have got weight fraction of water in kerosene that is initially present. So in the same way, we can get weight fraction of kerosene that will be left after the operation. So final ppm is 5. So therefore yn, small yn, which is weight fraction, final weight fraction, it will be 5 into 1 into 10 to the power minus 6. That is yn, small yn will be equal to 5 into 10 to the power minus 6. So in this way, we have converted ppm to weight fractions. Now this has to be converted to C. So we will be doing that next. So we got y0, small y0, 40 into 10 to the power minus 6. Then small yn, 5 into 10 to the power minus 6. Now small y and capital Y, they are related by this equation. Capital Y is equal to small y upon 1 minus y. How to get this equation, or what is this equation? For that you please watch my earlier videos. Therefore, if you have to get capital Y naught will be small y naught upon 1 minus small y naught. That is capital Y naught is equal to 40 into 10 to the power minus 6 divided by 1 minus 40 into 10 to the power minus 6. That gives capital Y naught as 4 into 10 to the power minus 5. Then similarly you can get capital Y naught, yn. capital Yn is small yn divided by 1 minus small yn. So therefore capital Yn is equal to small yn is 5 into 10 to the power minus 6. So capital Yn is equal to 5 into 10 to the power minus 6 divided by 1 minus 5 into 10 to the power minus 6. That is capital Yn is equal to 5 into 10 to the power minus 6. And once we got capital Y and capital Yn, capital Y0 and capital Yn, next would be, we will be converting capital Y's to C. So Y in this capital Y in this case is kg water per kg kerosene. Now we have to convert kg kerosene to meter cube kerosene. Kg kerosene to kg water, kg kerosene in the denominator, we have to convert it to meter cube kerosene. And C capital Y, because capital C is given in this way, kg water per meter cube kerosene. So that means if these two are multiplied, or let me tell you, if I multiply capital Y, which is a kg water per kg kerosene, if I multiply with density, which is kg, density of kerosene, kg kerosene per meter cube kerosene, density, because density is given to me. So if I do that, what is going to happen? Kg kerosene will go, and you are left with kg water per meter cube kerosene, and that is what we need. So that means if I multiply capital Y with rho, density of kerosene, I am going to get capital C. So in this way, the ppm data is converted to capital C. Let us move ahead. Okay, so first we will get capital C0. So capital C0 will be capital Y0 into rho. Simple. So rho is given to us, it is 783 kg per meter cube. So therefore C0 will be 4 into 10 to the power minus 5, because capital Y0 is 4 into 10 to the power minus 5. So 4 into 10 to the power minus 5 into 783. That is C0. This multiplication comes out to be 0.0313. Similarly, you can get capital Cn. So capital Cn will be capital Yn into rho. That is capital Cn is equal to 5 into 10 to the power minus 6 into 783. That is capital Cn is equal to 6.92 into 10 to the power minus 3. So in this way, we have converted concentrations from ppm to C. What is C? Kg water per meter cube kerosene. Let us move ahead. Now let us get the coordinates of the pinch point. What are the coordinates of the pinch point? Capital X1 max C0. So for that, as I told you earlier, you have a plot of C versus capital X, capital C versus capital X. Then the equilibrium curve is a straight line, because the equation of the equilibrium curve that is given to us, it is linear. So the point, the operating line will be starting at this point, which has coordinates of xn plus 1 cn, and then it will be intersecting the equilibrium curve at the concentrated end over here. So you get the pinch point, and coordinates of this pinch point are C0 and X1 max. Now objective is to get X1 max, because C0 is already known to us. So let us denote that as, let us denote the pinch point as point P. Now the equation of the equilibrium curve is 0.522 is equal to capital C upon capital X. So at the pinch point, what happens? The equilibrium curve is containing the pinch point. So the pinch point should satisfy this equation. So it will be 0.522 is equal to C0 upon X1 max. Very simple. C0 is known to 1. You just have to get X1 max. C naught is, we have got the value, it is 0.0313. So that is 0.522, that is equal to 0.0313 divided by x1 max. That is x1 max is equal to 0.0313 divided by 0.522, which gives us x1 max as 0.06. So we got x1 max. Now the only step left is to use this in the equation of the operating line and get the minimum adsorbent to solvent ratio. Let us move on. Now the equation of the operating line in the present form, it is capital C naught minus capital Cn divided by capital X1 minus capital Xn plus 1, that is equal to SS upon Ls. SS upon Ls, C naught is 0.0313, Cn is 3.92 into 10 to the power minus 3, Xn plus 1 is 0. Why it is 0? Because we are using fresh adsorbent, dry silica gel. It is not containing any water on its surface. So it will be 0.0313 minus 3.92 into 10 to the power minus 3. 3.92 into 10 to the power minus 3 divided by x1, capital X1 minus 0, that is equal to SS upon Ls. So that is 0.0274 by x1, that is equal to SS upon Ls. Let us continue with this equation. So we got this equation, 0.0274 divided by capital X1, that is equal to SS upon Ls. So at the pinch point where the operating line passes through the pinch point, since it is passing through the pinch point, so it will satisfy, the pinch point will satisfy the equation of the operating line. So it will be 0.0274 divided by x1 max is equal to SS minimum by Ls. X1 max we got, it is 0.6. So it will be 0.0274 divided by 0.6 is equal to SS minimum by Ls. That is SS minimum by Ls. It comes out to be 0.457. And that is what we have to report in this numerical. So in this way, we complete our calculations for this numerical. We have got the minimum adsorbent to solvent ratio that can be used in this operation. So I hope you have understood the steps that I have followed. If you have any doubt, you please mention that in the comment section. So let us stop for this video lecture. So thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. For now, thank you. Have a nice day and hope to see you soon in my next video lecture.